Right, so picking up from where we left off, so this is just to reemphasize that this is what we are dealing with, okay? And all of these statements follow, you just write, you just, disentangle just, this is just, I say I had x plus k hat z. Okay, write it down, independently, and all of these simply tumble out. There's nothing very significant about it. It's all straightforward algebra. I'm only giving you the gist of it. Okay, and this is important. Both the perpendicular and parallel, kinetic energy, you might say energy is a scalar quantity. What do you mean by parallel and perpendicular kinetic energy? What I mean is 1/2 mv perpendicular squared and 1/2 mv parallel squared. What parallel means along the z direction, perpendicular means along the x and y direction. That's what I mean. Both of these are conserved, and you can verify that. And it's no surprise, magnetic fields do no work. Here, there are no electric fields. We have specialized to E equals 0, right? Okay, so this is what we were saying. And from these two, okay, the solution to this equation is the solution to the equation dx double dot equals omega y dot and y double dot is equal to, I suppose, if I remember correctly, this is a negative sign. Yes. Okay, the solution to this is this. What do you do? How do you figure this out? You just take, for instance, you would, well, I'll leave you to figure that out. Okay, you integrate this. You just substitute for the y dot. You try to get an equation exclusively in x, and that's possible. Either that, or you substitute for the x dot, and you try to get the equation exclusively in terms of y. All right, and so you will find that if, as always, it's not so important to derive the solution itself. It's important to be convinced of the solution. So you plug this in here, and verify that this is indeed the case. And clearly, what this will say is that the motion in the perpendicular plane, in other words, the plane perpendicular to so the magnetic field is along the z direction, right? So the motion in the perpendicular plane is a circle. You see, the amplitudes are both the same, and one is a sine and the other one is a cosine. So, and sine squared plus cosine squared is 1, and therefore that's saying that so yeah, so that's essentially saying that it's a circle, right? So this is an alternative way of recognizing this. Recognize that B is 0, 0, B only along the z direction. I'll leave you to read this. Okay, I'll leave you to read this. It's just you can look at it this way, or you can look at it this way. The x naughts and y naughts are simply constants of integration. Okay, either way, the takeaway is just this. The motion in the perpendicular plane is circular. You already knew this. Okay, so this is just reinforcing what you knew in maybe slightly different notation, but that by itself is nothing. You just need to get used to it. That's all. Okay. Now, there are some interesting things to think about. You might not have had an opportunity. There's this thing called a pitch angle, which is this. Say you have a magnetic field pointing like this, yeah. like that. Now, the helical motion might be a very tight helix, right? Or it might be a loose helix, like that. And the thing distinguishing these two is if you can draw a tangent from here, this, okay, this theta is what's called the pitch angle. It's similar to the pitch of a screw. Right? How, for one turn of a screw, you have a screw, for instance. I don't know, that would be a pointed tip, and you have several engravings. So for several engravings on the screw, and so for one turn of the screw, in one turn, how far does it advance? That's the pitch of the screw, right? You can. It depends upon how closely graduated the markings are on the screw. So it's the same concept. So this is the pitch angle. It is essentially the tan. I believe the tan theta is equal to V perpendicular. Sorry, V perpendicular divided by V parallel. And for small theta, theta is something approximately equal to V perpendicular to V over V parallel. Okay, so how fast is the V in comparison, how fast is the V along the magnetic field in comparison to the V perpendicular to the magnetic field? So these are things that you can think about a little more. Okay, not only, and if there was no V parallel at all, okay, it would simply stay in the circle, it would not advance at all. Okay, and so that's the pitch angle. You can think about this. You can think about the relation to the instantaneous radius of curvature. So these are interesting variants that you might or might not have come across before. The straightforward lawnmower radius and things like this. This you have definitely encountered before. Okay, right, and I have to get this guy to move. I don't know why it's not moving. It's stuck to the. Okay, sorry. Right. Okay, so now let's introduce an electric field. As such, you'll immediately look at this and you'll immediately say, oh, what's the big deal? I knew this, right? This is A, right? A is equal to just the charge times the parallel component of the electric field. That's it. If there's a perpendicular electric field, it's not going to do anything. All right. So, well, no, sorry. I beg your pardon. There will be a perpendicular. The electric field does things in both directions. The magnetic field acts only on the perpendicular component of the velocity. Parallel is always, parallel refers to B. Okay, i.e. along B, parallel to B. That's what parallel refers to. Okay, and the perpendicular, you have the usual electric field and you have the Lorentz force. In the parallel direction, there's no Lorentz force, right? So there's nothing remarkable about the parallel motion. As regards the perpendicular motion, let us anticipate, okay, and so this is where things start getting interesting. Again, there's nothing terribly new about this, but it's you might be seeing it presented this way for the first time, okay. Let us anticipate, and this treatment is due to Starok. that it can be split into a time dependent and a time independent part. This would be the time independent part, there's no time dependence here, and this would be the time dependent part. I would say this would be fast motion and this would be slow. Nothing is truly time independent, right? So it's just that the time scales that you're talking about here are much slower than the time scales that you're talking about here. So let us anticipate this and let's split up the V perpendicular into like this. Okay. Now, the time dependent part, this is the usual gyro motion, okay, that we discussed. Nothing different. The time independent part is a novel thing, is a new thing, and this is what's called, it's a slow, like we discussed, this is a slow motion, and this is what's called drift. Okay, due to the presence of the electric field, you have something called, you have a new a phenomenon called the drift, and we will see what this is. So you substitute this, in here. Okay, no, just in here. Okay, that you don't have to worry about that. So you substitute in this in here. Okay, and you separate out the time independent and dependent parts, obviously, right? So this would be this does not have any time. So you just you can only equate the time dependent part to the time dependent part, time dependent LHS to the time dependent RHS, time independent LHS to time independent RHS. Okay, so for instance here when you write d over dt, V perpendicular would be Vd plus Vgt, right? And because this is time independent, this goes to 0. So you only have like that. Okay, so you only have d over dt of Vgt on the left hand side, and so similarly. So and so you equate the LHS and RHS, time dependent with time dependent, time independent with time independent, like that. And the time dependent part yields the usual gyro motion. The time independent part yields the interesting E cross B drift. Okay, the 0 is from the RH is from here because d over dt of Vd is 0, and so this entire thing. So you have this E perpendicular plus 1 over C. By the way, if you're wondering where this 1 over C came from, this is because Starok likes to work in CGS units, as do I. So that's where it came from. Right. So and this is the interesting drift velocity crossing. Okay. Now what you do is you cross this entire equation with B. B cross this. You cross the entire equation with B. Okay. And you do the vector algebra carefully, and you get that the drift velocity is perpendicular to both the direction of E as well as B, and it goes like this. Very, very important. Okay, the algebra is simple, but the result is very important. So this is the drift velocity. In the presence of crossed electric and magnetic field, you see, electric and magnetic fields which have a non-zero cross product. In other words, if there's a component of the electric and magnetic field that are perpendicular to each other, you will have a drift, which the direction of which is perpendicular to both the electric field as well as the magnetic field. Interesting result. And let us see its implications. Right. So you see, if you have crossed electric and magnetic fields, you can verify that electrons and protons drift in the same direction. Very important to understand this. Why is this? You see, there is no Q here. The Q does not enter. the E, whether you know the sign of E does not enter. Okay, the drift does not care about the sign of the charge. Independent of, in fact, is simply independent of charge and its sign. Okay, so electrons and protons drift in the same direction. Yeah. So here are and this is from Boyd and Sanderson. Okay. Not only that, not only the fact that electrons and protons. So these will be protons, positive charges, negative charges. They are both drifting in the same direction. Okay. What you have here is that when so this would be, I mean, the gyration speed, and this would be the drift speed. Okay, now you can immediately sort of the magnetic field is pointing out of the page, and the electric field is pointing in the z direction. That's why they're crossed, right? And you can immediately sort of intuitively discern that there can be a few different limits. Okay. One is if the drift is slow, so that you are allowing for an entire gyration to happen, like that. So the gyration is happening. The gyro radii might well be different, but the drift is in the same direction, like this. And the direction of the drift is perpendicular to E as well as B. Because the B is pointing out of the page, you have the basic gyration around the B. Okay, but the drift is not because, you know, there's the drift is not because of the velocity parallel to B. That would be you know, into the plane of the paper or out of the plane of the paper. That is not, this is not a V parallel. This is really a drift velocity, and the drift velocity, as you can see, is perpendicular to the direction pointing out of the paper, as well as this. It's in this direction. Now, the drift can be such that you are allowing it. If the drift is slow, okay, you can allow for entire gyrations to happen like this. If the drift is relatively faster, if u is equal to ve, you can it will not be able to complete an entire gyration. Before it completes an entire gyration, it's forced to drift, and in the other, you know, if the drift is fast, this would be the drift velocity. If the drift is fast in comparison to the gyration speed, then you have, you would have this kind of thing, where, you know, even this amount of gyration is not able to be completed, and you would have, okay. So yeah, so this would be the drift velocity. And this would be. So this gives you a qualitative feel for how things can be. Okay, when the gyration speed is less, or, you know, equal to, or even greater than the drift speed, that would be the greater than the drift speed. And this would be much less than the drift speed. Okay, so these are interesting, you know, limits. Okay, now. How about, for instance, you would have the usual Lorentz force like this. How about if you have gravity instead of instead of an electric field? As such, you know, gravity and electric fields similar. They just, you know, result in a force parallel to the direction of motion. Okay, but there's one important difference. So that's why we're able to write down the thing. But there's one important difference. Gravity cares about the mass of the particle. Electric fields care only about the charge of the particle. Okay, so simply because of this, you can and given the fact that we already understand drifts in crossed electric and magnetic fields, we can immediately write down how what kinds of drifts you would expect in crossed gravitational and magnetic fields. Okay, by simply analogy with the electric field, the effective electric field, we can replace this G with an effective electric field like that. This is the only difference. Okay, and if you plug this in here, you'll immediately see that the force cares only about the mass and not about the charge. That's why you have this. I cannot explain this too well. I mean, this is how I think. I mean, you really have to convince yourself. Okay, that if you wanted to write this as an E times E, if you wanted to force that, E times E effective, if you wanted to write this as that, then this would be what E effective is, right? This is E here. Okay, then you can simply write down the exact, instead of this E, I have another kind of E effective. I have another E rather. And then what happens is the drift velocity depends on the mass as well as the charge. Unlike the case for a pure electric field. It depends both on the mass and the charge. And what's more, there will now be a net current. Okay, a current given by say N E V D, like that. Okay, that would be this. And it's interesting to think about which species carries most of the current. This rho would be your NE, and so which species meaning electrons or protons. Normally, you think of in everyday life and whatever, current is carried by the electrons, right? The protons are sluggish. They're hanging around. It's the electrons, the mobile electrons that go around carrying the current. So in this case, is that correct? This kind of drift current, does that, is it the same? Think about it. The answer might surprise you. And because of this, this drift velocity does care about the sign of the charge. It does care about whether the E is positive or negative. Therefore, electrons and protons, so if you have a downward directed gravitational field and a B pointing out of the page, electrons and protons drift in opposite directions in crossed gravitational and magnetic fields. Okay, so that's right. So now when we resume, we will. So far we have kind of introduced time varying. We have kind of introduced time dependence in a rather crude way. In that we have talked about slow drifts. Okay, we have talked about slow drifts like this. We have, but we have not talked about any what should I say? Any spatial variations of either the electric or the magnetic fields. Okay, so we will the next level of complication we will consider is when we talk about inhomogeneous. Inhomogeneous meaning spatially varying. But not very strongly so. Okay, spatially varying meaning d over dx kind of thing is not equal to 0. Okay, magnetic fields, for just to keep things simple, we will not consider any time we will not d over dt we will keep to be equal to 0. Okay. So it's important to consider these things in their respective limits so that we get a clear idea of what's going on physics-wise. And then, as and when you come to a real situation, you put it all together, and most of the time you will not be able to solve it with pen and paper. You will have to resort to a computer.